Okay, so now that we've talked about voltage sources as batteries, generators, or your electrical power plant, all of these are voltage sources that are provided to be able to make electrons flow through a wire. Now we're going to talk about resistance to flow. And we mentioned that in the last slide, the end of the last lecture, where we talked about the fact that if I have a line that is either very, very small in diameter or it is extremely long in length, then this is going to add drag or resistance to the water flow. Similarly, we can make materials that are intentionally resistant to or electron flow through them, which effectively increases the resistivity of the circuit by impeding the flow of electrons. So we would use something other than a conductor here. We would use a material that might conduct very poorly compared to copper, for example. These materials can be used to resist or to increase the rate of collisions as the electrons try to make it through the circuit. And the symbol for these type of materials is given by the squiggly line. And when you see one like that, a sawtooth-like form drawn on a sheet of paper, then that's a symbol for a resistor that has been added. And many devices have resistors already on them. You don't need to add them. For example, if you want a heat generator, like an electric light bulb, or an oven, or a toaster, or a hair dryer, they have resistors that are part of their circuit anyway because they have to generate heat in order for them to work. One of the aspects of resistors is that they will increase the heating up of a device when current or electrons flow through them. So factors affecting electrical resistance, well, first, they're inversely proportional to cross-sectional area. Thin wires are more resistant than thick wires. We also said that we could change the composition of the wire to make it more resistive as well. It doesn't have to be pure copper, aluminum, or gold, silver, etc., but they can have materials that are much more resistant to electrons, such as insulators, for example. Secondly, the resistance is directly proportional to length. If I double the length of the wire in a circuit, even if the wire is all made up of a conductor, then that will double the resistance, and that will impede the flow of current. Every time I add resistance in the wire or in a circuit, the current will drop. Right? It will drop for assuming that the voltage source is the same. So for the same voltage, by making the doubling the length of the wire or making it thinner, that will both increase the resistance. Both of those will lower the amount of current. Materials such as rubber are much more resistant than copper of the same size. Rubber, as we've said, is an insulator in the category with glass and plastic and fur and hair and those type of materials. Not that those are not really used in electric resistors, but they're mentioned here just for completeness. Now, one of the things that does heat up and generate a lot of resistance is the electric light bulb. Factors that affect the resistance are its temperature, and the temperature will be controlled by how much current goes through it. It will be controlled by how much current goes through it, and it will be controlled by the resistivity of the wire. The higher the resistance of the wire, then for given voltage, we generate more heat. Or I should say that maybe a little differently, that for constant current, higher resistance will generate more heat. So the higher the temperature, generally speaking, for conductors, and in this case a filament is a conductor. It was designed by Edison as the first electric light bulb by finding the magic material that he chose and selected, which was tungsten, which has been used almost continuously since the invention of the electric light bulb. And you can see that when you screw on the base is an insulator. It separates electrically. There's no conductivity between the wire coming in at the base and the wire coming out at the base. And the two ends of these wires there's a non-conductive gap, right, that you see at the base that separates that, so that any voltage difference that goes into, if I put a positive voltage on one side and negative on the other, the current has to go through the filament. It cannot cross the insulator. We want the current to flow in the filament. the filament has to heat up. When it gets hot enough, then of course we get light. In the development of all this was what was discovered by a German physicist by the name of George Ohm, that there was a relationship between voltage, current, and resistance in a closed circuit. And stated precisely, it says that the current in a circuit varies in proportion to the voltage. So that makes sense. If I double the voltage, I've doubled the pressure that is pushing electrons through the loop, so therefore that will increase the current flow. And it's inversely proportional to the resistance, namely to say, if I double the length of wire in the circuit, assuming the wire is the only resistor, then I will double the resistance and the current will go in half. There's a direct proportionality between current and voltage, and the current is inversely proportional to the resistance. So we can state that mathematically, and there's an equation for that. It says that the current in the wire measured in amperes is equal to the applied voltage, which is often given either by the battery or the generator. If it's the wall power, it's 120 volts. It's the current is the voltage divided by the resistance. The resistance, if it's a light bulb, will be, of course, the resistance of the bulb itself. If it's a toaster in the kitchen, then there will be the resistance in the coils that also generate heat to make the toast nice and warm and cook well. But the relationship is very simple. Current is voltage divided by resistance. So example, for a constant resistance, current will be twice as much for twice the voltage. And for twice the resistance and twice the voltage, the current will be unchanged. Makes sense. If I have twice the resistance and don't change the voltage, then the current will go down to half of its original value. And the purpose of resistors and circuits are to limit the current inside the devices. It's also often used to generate heat, which is what you need in a hairdryer, a toaster, or a light bulb. And those resistors come as part of the device that's causing the light or heat to occur. We don't have to add them in as extra elements. Now, we talked a little bit about the difference between direct current and alternating current. So this is a picture basically showing what the two looks like. If I have what I would call a DC, which means it's a constant voltage source, then the current will, through the circuit or through the wire, will also be constant, and it will be inversely proportional to the resistance, because remember we said that current is equal to voltage. This is the DC voltage, what we would call direct current, divided by the resistor. In this case, the current flows only in one direction, the direction that's given by the polarities on the battery that the ends of the wires are connected to. Electrons always move from the negative terminal towards the positive. Opposites attract, like charges repel. This defines the direction of electrons in the circuit. But with alternating current, so I can imagine now, in this case, this is not a battery that you can buy at the store. You cannot buy a 12-volt alternating current. You can only buy a 12-volt DC current, which means DC is often meant, even though it stands for direct current, it means any condition in which the parameter does not change with time. So direct current, DC, could refer to voltage or it could refer to current. It's any parameter that's not changing with time. Alternating current, on the other hand, has the property that the current is going up and down with time. In this case, if the voltage that's driving the current has this sine wave going up and down from positive volts to negative volts, then the current will also go from positive to negative and follow the direction of the applied voltage. And this is basically the difference. So now you can think and see quite clearly the difference between DC and alternating current. Now, as we've stated before, when you plug your device into the wall, you are basically looking at a oscillating voltage source that varies by 120 volts. Actually, this is a little bit incorrect. The reason is I put this here is because everyone is familiar with 120 volts. But the actual waveform itself, if we go back one, that comes out of the wall, actually, if this was voltage instead of current, this would go to 170 volts down to minus 170 to plus 170 to minus 170. The actual peak value is 170 volts coming out of the wall. But the average voltage, if I take the average, if I square this, the negative flips up to a positive, the average value is 120 volts. So we call it 120 volts even though the peak to peak is plus 170 to minus 170 out of the wall. And this happens at 60 cycles per second. And this is, of course, where we get our power. In Europe, they've adopted the 220 volts as its standard. And by the way, as a result, their current that is generated in those devices is quite a bit smaller than ours. So we'll learn in the next slide that power, which is what we need to make something hot or bright or do what we want, is really the product of voltage times current. You can get the same effect at a lower voltage if you apply higher current, or in the opposite sense, if I go to higher voltage, I can get the same effect of the device by using a lower current, because it's the product of the two, as we will see, that actually makes gives the what's called the power, the electrical power of the circuit. This is where we have their frequency. By the way, I believe they work at 50 hertz, 50 cycles per second instead of 60, but I'm going on memory from that, but it's very, very close. But their voltage coming out of the wall is quite a bit higher. Converting AC to DC. As you know, in all of the apparatuses that we use that require power, such as the camera that is videotaping this lecture, it runs on a 12 volt power source. And it gets its 12 volt power from the wall that comes out at 120. So we have a device called a transformer that when you plug in your wire into the wall to charge your battery on your device or run your camera or to charge your laptop computer, it is generally downgraded to 12 volts from a DC from an initial input of 120 volts AC. And it's done with devices that we're not going to talk much about called diodes. I have a circuit in the next slide, I believe it shows that. But the basic idea is that diodes are a device that only allows current to flow in one direction. So if you change the polarity of the voltage, the current stops. That's the basic function of a diode. And the way we generate this 12 volt output is starting with the power from the wall over here. So here's our voltage output that goes from plus or minus 120 volt, or 100 in this case, 120 volts. There's a transformer that we call it a step down transformer that takes it down to 12 volts. And the output of that is a wave that goes up and down only between 0 and plus 12. It oscillates up and down. And as discussed in your book, if you put a capacitor at the end of the circuit, then it actually has the effect of smoothing the voltage so that before the voltage can drop back to 0, the next pulse comes along and keeps it bumped up again. Converting AC to DC involves this capacitor. First, it involves the diode that only allows current through in one direction. There's this discharging and charging capacitor, which helps to provide continuous and smoother voltage as well as current. And the pair of diodes is used so there are no gaps in the current output. Now, we're not going to go through all the details of that. I spent about 30 minutes in a sophomore class for engineers describing how this system works. But the idea is that these diodes are very good at only letting through the current in one direction, and that can be used to make the voltage output unipolar instead of bipolar. When we flip the light switch on a wall for the circuit, so imagine that you do exactly that. You have your light switch on the wall. Then what is happening is that circuit that is now what becomes a continuous closed loop of conductor that go through a light bulb that we showed earlier. When this happens, electric field is established inside the conductor going from the plug in the outlet or the power source of the outlet all the way through the conductor and back around. One might think that as a result of this that we've now established electric field in here, the electrons are free to zip and continue to move through in a straight line all the way to their destination, and that the electrons will move instantaneously across the conductor. Well, this is in fact not true at all. The electric field, the voltage is established instantaneously when we flip the switch that closes the circuit, but the electrons themselves undergo random motion with some migration in the correct direction, but every time they bounce or they hit an object, a nucleus of the copper molecule, they ricochet, which tends to randomize their direction. Now, on average, they will keep moving in the right direction given by the electric field. this electron is going from, which was originally here, is slowly migrating across, but it's doing so at a very slow pace because it's going through all these collision parameters, the collision effects that tend to slow it down. So the current is established through the wire very, very quickly, but what is happening is not that the electrons are moving quickly, but all the electrons are moving slowly. And so as long as the electrons are moving at different parts of the wire instantaneously, then it doesn't really matter too much how fast, whether they're moving extremely fast or extremely slow. When you flip the switch on the wire, it's the voltage or the electric field through the wire that switches on instantaneously. The electrons move at a much slower speed, but they are moving everywhere from the beginning of the wire to the end of the wire. But they're all moving in unison across the wire at a much slower speed than what you see as a result of the electric field or the switch. So speed and source of electrons in a circuit. If the voltage source is DC, like for example a battery that we've been discussing, these batteries right here you see are DC. This looks very much like a 12-volt battery that you would place in your car with a positive and negative terminal. The battery, when you connect a wire across here, as you see in the figure on the right, the electric field is concentrated primarily inside the copper. So the copper provides a conduit for electric field, and there's a much lower electric field circulating in free space outside as a result of these terminals, positive and negative charge, but most electric field is conducted or is constrained, is within the metal structure of the wire itself. The conduction electrons are accelerated by the field. The field is generated by the positive and the negative terminals. The field always goes from positive to negative. And remember, electrons go the opposite direction. They go against the field. They go from negative to positive. But the conduction electrons are accelerated by this field in a direction parallel to the field lines and parallel to the wire itself. Before they can gain appreciable speed, however, they bump into the anchored metallic ions in their paths, transfer some of their kinetic energy to them, begin this random walk problem. This is where it starts here and then eventually migrates up over to here in a much slower velocity than would actually be happening. But we still get current as long as there is a positive motion here. It does not have to move at the speed of light. It only has to move, we only have to have enough of these electrons crossing a cross-sectional area every second. And we can do that by having 1,000,000 of them traveling very, very slow, or a couple of them traveling very fast. Either way, we do that, and typically the way we do it is by having millions of them traveling very, very slow. That will still generate the same current as a few charges moving very, very, very fast. So it works about fine in terms of current. We still get the current even though we can still make a very high current even though the velocity of electrons is very slow, simply because there are so many of them moving. Okay, so for the end of this lecture, we're going to talk about misconceptions. What are the misconceptions about electric current? We've talked about some of them already, but we'll review. Current is propagated through the wires by electrons bumping into one another. No, not true. Electrons that are free to move in a conductor are accelerated by the electric field impressed upon them. That's one thing to notice. It's true that they do bump into one another, and they bump into the fixed the nucleus of each of the atoms, but this slows them down and offers resistance to their motion. So that's the other factor to keep in mind. And electrons throughout the wire, throughout the entire closed path of the circuit, all react simultaneously to the electric field. It's just that they're all moving very slowly. So when you flick the switch, the electrons on the near the positive terminal of the voltage source are starting to move, but so are the ones everywhere else in the circuit. They all react simultaneously to the electric field. Another misconception, electrical outlets in the walls of the home are a source of electrons. No, the outlets in homes are alternating current. Electrons make no net migration through a wire in an AC circuit. It's also true that when you buy the wire from the store, it comes as a conductor with all the electrons in it. So we're not adding electrons to the wire when we make a current. We are simply making the ones that are already there move slowly. Now, it's true that as they come off of one end of the wire, we have to add more at the other end. That much is true, but the source of the electrons is not at the outlets. Now, when you plug a lamp into an outlet, the energy flows from the outlet into the lamp, not the electrons. So basically, what that means is that because it's an alternating current and the electrons are simply moving back and forth about their equilibrium place, then they are not migrating from the outlet into the lamp, but rather it is the kinetic energy or the energy of the electrons that is, which is their flow, which is causing the sensation of electric current. And the other point to keep in mind is that electrical utility companies sell you energy, but they don't sell you the electrons that produce the energy. Okay, so with that, we'll move on to the next section and pick up at the next lecture.